All right, in this video, we're going to take a look at another related rate problem which uses similar triangles. So let's get right into it. A water tank is in the shape of an inverted cone whose height is 5 meters and has a radius at the top of 3 meters. If water is flowing out of the cone at 1 meter cubed per minute, then find the rate at which the water level is changing when the water is 2 meters deep. All right, remember that our first key step in solving any related rate problem is to find the rates of change within the problem. Again, we can identify these by rates of change. They say change, increasing, decreasing, or simply by the units themselves. So right here I see a 1 meters cubed per minute. Okay, and I can write that down, 1 meters cubed per minute. And again, I can use the units themselves to kind of tell me what my derivative is. Meters cubed on the top, that's a unit of volume. So this should be a change in volume. And per minute is a unit of time. So dV dt. Now if we read a little bit closer, it says the water is flowing out. So that means that my volume is changing in a negative manner, that the volume is getting less. So I need to put a negative 1 meter cubed per minute. So my change of volume per unit of time is negative 1 meters cubed per minute. All right, now the question itself in a related rate problem is also a rate of change. It's asking at what rate is the water level changing, okay? So for the water level here, it's talking about the height of the water because we're talking about a cone going up and down. So I'm gonna say that dH dt is equal to question mark. All right, so these are the only two rates of change that are given in the problem. So I wanna square these off. Okay, and then we'll move on to our second key step in a related rate problem. All right, so our second key step in solving a related rate problem is to find a relation between the rates of change in your problem. So this is talking about the volume and the height of the water, which is sitting inside of a cone. And the volume of a cone is a known formula. We can just look that up. It is volume is equal to 1/3 pi r squared times h. All right, so this is an initial equation that we can use. However, if you notice, there's volume which is changing, there's height which is changing, but there's also a radius in there. And the problem doesn't tell us how fast the radius is changing, nor does it ask how fast it's changing. So we really want to get rid of that radius in this equation. And how do we do that? Well, we use the fact that the water is sitting inside of a cone, which they say is initially 5 feet high, and has a radius at the top of 3 meters. Okay, and then the water has to sit inside of here at a given radius and a given height. And because it's sitting inside this cone, the radius and the height will be in the same proportion as the outside cone. So we get an equation like r over h is in the same proportion as 3 over 5. And then we can solve this for r by multiplying h over, and we'll get r is equal to 3h over 5, and then we can take that and plug it in for r in our equation for a cone. So 3h over 5 will get plugged into the volume of the cone. All right, so let's do that algebra. We'll get our volume is equal to 1/3 pi. Instead of r, we'll write 3h over 5 all squared times another h. We can simplify this, so we'll get 1/3 pi. We'll square 3h over 5, giving us 9h squared over 25 times another h here. And if we multiply all these numbers out, we'll end up with 3 over 25 pi, and then multiplying our h's, h cubed. So there's an equation that relates together the only things that they ask about or care about in this problem that are changing, volume and height. All right, so our third key step of solving any related rate problem is once we found this equation relating together the volume and the height, we're going to take the derivative of this equation with respect to time. And remember, all of your derivatives in related rate problems are d dt. Now, when we do this, we're just going to apply implicit differentiation, so our normal derivative rules, and anytime we take the derivative of a variable, we're going to tack on that variable dt. So for example, the derivative on the left-hand side, the derivative of v, is just 1, and then dv dt. Okay. On the right hand side, 3 over 25 pi, those are just numbers, they just sit there. And the derivative h cubed is 3h squared, and then dh dt. Okay, so there's our derivative, and the final step now is just to plug in all the known values and then simplify and solve. All right, so let's try plugging in these values. dv dt is equal to -1. Okay, 3/25 pi is just 3/25 pi times 3, and then h squared. Let's look through the problem. Where is h? Well, it's the height level of the water, and it says that the water is 2 meters deep when this is occurring. So we're going to plug in 2 for h, and all that leaves us with is dh dt, and remember that's what we're solving for. All right, so now it's just a matter of arithmetic. So we're going to get -1 is equal to, and if we multiply all these numbers together, we're going to get 36 pi over 25 times dh dt. Okay, and then multiplying by the reciprocal to both sides, we'll get that dh dt is equal to -25 over 36 pi. And now we can attach the units, which is going to be the units of height is meters, and the unit of time in this problem is minutes. So there is our final answer.